All right, so this slide is about deflection, right? Deflection criteria. To avoid damage to finishes, ceilings, partitions, amongst others, the deflection of timber flexural members when fully loaded should be limited to 0.003 times the span. So this is a thumb rule that we normally use. However, for longer span, by longer span, we basically infer to spans greater than 4.67 meters. All right, the maximum deflection should not exceed 14 millimeters. All right, so this is another condition that you have to bear in mind. You have to look at thoroughly. All right. Now, generally, the thumb rule is that the deflection should be within 0.003 times the span. For long span domestic, it should be 0.003 times the span, but not greater than 14 millimeters. So these are the two conditions you need to follow, you need to abide when you're checking the deflection criterion. For a flexural member to be adequate in deflection, the sum of the actual deflection due to bending and that due to shear must not be greater than the permissible deflection, right? So the deflection due to bending, right, due to moment and due to shear should be within the permissible range, both of them together. Now, the actual bending deflection is calculated using the following formulae, depending on whether you're dealing with a uniformly distributed load or a point load. Now, for a uniformly distributed load, the deflection is determined using the formula 5 times WL cubed over 384 EI. Now, you have to bear in mind that the W, capital W, provided in the formula stands for a UDL multiplied by L. So if you were to put it in the UDL version, it would have been 5WL4 over 384 EI. For a central point load, the deflection at midspan due to the moment is going to be WL cubed over 48 EI, where E stands for the Young's modulus and I is the second moment of inertia of that section. Right? So the Young's modulus value to be adopted is the minimum Young's modulus used for isolated members, and the Young's modulus mean should be used for truss members when specifically you have load sharing amongst the different members. So you have to be careful with the E value you are using. So you have to pay attention. So the E value, normally you've got a minimum and a maximum value. So you use the minimum for isolated members, but when you have members that are load sharing, then you go for the mean value for the Young's modulus. All right, so now we look at the actual deflection due to shear on rectangular and even square cross-sectional timber members. Now, the deflection due to shear is calculated using the formula provided below, that is the shape factor multiplied by the midspan moment, that is the maximum moment, divided by the section area multiplied by the modulus of rigidity or shear modulus, right? So this is the formula you use to determine the shear deflection. Now again, just to summarize on the formula, M is the mid-span bending moment, the maximum bending moment you have, you witness, you can determine at mid-span. S is the member shape factor, which is 1.2 for rectangular sections, right? For other shape, you have to refer to B as 50 to 68. Capital A is the cross-section area, right? So if it is a rectangle, it is B times D. If it is a square, it is B square. And G is the modulus of rigidity or shear modulus, which is taken as the Young's modulus divided by 16. So the modulus of rigidity is 1/16 of the Young's modulus. All right. Now, again, here you have to be very careful whether you're dealing with an isolated member or a member which is sharing load. So if it is an isolated member, your Young's modulus value would be E minimum. And if you're dealing with load-sharing members, then the Young's modulus should be taken as the mean Young modulus. Sorry. The expression can be rewritten to include the values for S and J as follows. So the the shear deflection, which is SM over AG, is equal to, now if we factor in the shape, factor 1.2, and we know that the modulus is 1/16 of the Young's modulus, so it now becomes 1.2 m over AE by 16. Now when we rearrange it, we get 19.2 m over AE. So this becomes our formula to be used for the determination of deflection due to shear forces. So the total actual deflection resulting from bending and shear will therefore be the summation of the following relevant formulae. So the actual deflection is the sum of the bending deflection and the shear deflection. Now, again, we have to consider two possibilities. One, if we have a UDL, then the actual deflection is going to be equal to 5 times WL cube over 384 EI plus 19.2 M over AE. Now you have to also bear in mind that capital W in the UDL formula is the UDL small w times capital L. For point loads, the deflection is WL cube over 48 EI plus 19.2 M over AE. So from this refined formula, you're going to determine the actual deflection witnessed in members which is subject to either a UDL or to a point load.